Very good, very good. So so far our timing is very good. So I have talked to I have asked the class in last lecture whether our class pace is okay or not. So, all the comments I received is okay. So far the pace is fair. So then in this case, there one student earlier told me that maybe we can make the pace to be faster. So in this case, because most of the class members enjoy current pace, I will keep the current pace for now. But whenever you find that we can go even faster, or sometimes if you feel we can go slower, please let me know immediately. And then we can adjust the pace for you, okay? So then everybody will get to the correct experience, good experience in the learning, okay? So can you hear me, guys? And when you join, please mute yourself. Yeah. Very good. Yes. Please ask.
So like I have a vibrations exam tomorrow from like 11:40 till 12:50. Okay. So that overlaps with this one. So what am I supposed to do?
Wednesday, right?
Yeah, wait. I mean not tomorrow, Wednesday. Yeah, my bad.
That's fine. So you on the class in the Wednesday is our midterm exam number 1. And we will show, the TA will show the exam sheet at the beginning at 12:50 around that time. So you go ahead to take the exam. If you and then you know all the questions there, 3 questions. So if you find that you need more time, write down take a snapshot of the exam sheet, and we will post it on the canvas as well. Then you leave for other things. After you come back, from other classes, you can resume it and then send it to TA. Just explain to him that that's fine. Don't worry about it.
All right, thank you very much.
Sure. You are very welcome, And all the students, actually, you make sure all those exams, quiz are used for you to practice, to know that whether you can solve those questions independently by yourself or not. Okay, so no pressure at all. No pressure. Enjoy the class. Okay. Okay. I saw the Nicholas has a question. Okay, fine. It's for Aaron. Okay, fine. Yeah, good. So, very good. Today we will have a quiz at 1:15, and the TA will show the questions to you. And then, same way, if you need more time, you can do that. That's fine. But make sure don't talk to each other during the exam and the quiz, because this is for you to find out whether you can solve problem independently or not. Okay, this is benefiting you. So do it by yourself. Homework, you can do it in a group. That's fine. Okay. So I hope all of you take those opportunities to practice. And currently we have already finished the direct method. This is one of the fundamental part, and we went through it in a reasonable pace, because we want to I want to make sure all of you can solve those questions by yourself or by hand. Okay, so then we went through it carefully and slowly. And in the future lectures, we will reasonably increase the speed. And if you have good foundations there, then you should have 0 problem. Okay, very good. So ask me if you have any questions regarding to the quiz. I saw a question, Catherine. Yes, open notes. All the electron notes can be opened. That's fine. You don't need to memorize anything, but some concepts you should already understand. You should understand it, and then when you write it in your own language, and then to show that you indeed understand, then it's fine. Yeah, even for the midterm exam. Yes, 10. Yes, yeah, for the midterm exam, final exam in the future, and for all the quiz, open book, open notes. So you need to understand the material, and then be able to do the homework by yourself. Then you should be okay. Very good. So in terms of logistics, can you guys see my shared screen? Yes. Okay. I saw a question from Davis. Can we use some? You don't need to. We don't need the MATLAB. You can use it, but that's not the purpose. The purpose is for you to practice. those simple mathematics, understand how to do the questions. Then if you use MATLAB, you solve the eigenvalue, eigenvectors, then what's the point? Everybody can use MATLAB, right? So Davis, don't use that. Not helpful for you. Okay. Even for the some finite element question, I list like direct method spring system. You can use Abacus software to solve those simple questions. But then what's the point? The point is letting you learn things. If you use the software, then you don't learn things, right? So that's the key. Yeah. Very good. Very good. So if you see you might see my screen here. The logistics is same as the previous one. We're all on the same page now. That's great. Excellent. Today's class, we will stop at 1:15, and then you can start to take the quiz number 1. Okay. So, okay, good. So you can go through the logistic items here. Make sure you follow the timing, and I list all the important timing in the blue color. So make sure you follow this timing. And also for the exam, I already listed the topics we are going to test. So you make sure when you review the material, understand the material, and especially with the focus on those topics. Okay. Good. Very good. Very good. Okay. And this is the schedule for the rest of semester. So Wednesday we will have exam number 1. After the Wednesday, the Friday we don't meet on the Zoom. You will watch the online video tutorial. Next week, for Monday we will meet in person. We will meet in the classroom. Dr. Feng will give a very exciting talk on his research. Okay, and this is used to open your horizon, and you can find many many engineering problems can actually be benefited from finite element, from the numeric method, from the concepts we discussed in the class. Okay, there can be multi-physics problems. And then next Wednesday and Friday, we also don't meet in the Zoom. You will also watch the tutorial. So basically, by the end of this month, you will watch 3 tutorials, and then we will upload 2 more tutorials to replace these 3 videos. And then we will give you the project. You can use the Abacus to solve the project. And in the same time, in the classroom, we will discuss about the fundamental concepts of the finite element. And then you will learn more how the software works, what's the mathematical indeed working behind the computer screen. Okay. I saw a question from Nolan. So we do not need, yes, we do not need to submit homework number 1. We will start with the homework number 2. That created submission might be the misunderstanding. Don't worry about it. I already write it in the announcement in the screen. No need to submit. Okay. Very good. Very good. Ask those questions to clarify. Sure. Follow what I said in the logistics at the beginning of every lecture. So that is to bring all of you to the updated status. Okay. Excellent. So here is the schedule, and many of you send me very constructive, very positive comments after the class, the survey. It seems you guys are doing very well. You guys are enjoying the class and learning the interesting things. That's good. I'm very glad that you send me those positive comments. And if you have other question, concern, also let me know. Okay. So then we can work together to make the class to be great. Yeah. Very good. Thank you. Thanks for all the students who have sent me the comments already. Yeah, very good. For those who have not sent to me, you can do it anytime. Okay, no pressure. Anytime you can let me know your suggestions, the comments. Very good. So today we will talk about the uniaxial bar element. Okay, so in the previous lecture, we have already gone through the mathematics and the direct method, and now we can go one step further to talk about another important topic, is called a uniaxial bar element. Okay, so to talk about that, initially we need to know several concepts. So we discussed about those concepts in the last lecture now. So let me just briefly go through the key point here. So in this area, when we talk about the uniaxial bar area, we need to understand the key concepts of mechanics of material. So firstly, the bar is different from beam. Bar actually is a long, slender object. It has a certain length that's called L, original length, and it has certain area called A, cross-section area, A, capital A. When the force is applied, here the force is the capital P. When the force is applied to this bar, then it can be elongated or compressed, depending on the force is a tension or compression. And then the length of the bar will change. The length is delta. Do you guys see my mouse? See my mouse?
Yes.
Okay, very good. Let me change to red laser. Good. So this delta is net change of the bar around the axial direction. It can be positive or negative if the force is tension or compression. Okay, so this material is not rigid anymore. It can be deformed. It's like this rubber bar, a rubber beam, right? A rubber band. So it can be stretched. It can be stretched. If this material is slightly, you can also compress it before buckling. The rubber band can also be compressed a little bit, right? So that's the example of a slender bar. And then here the A also change actually. The area will also change because the material is conserved. If you apply the force to deform it, the area also change. Okay, so area will change, length will change, force is applied to this guy, and then those different quantities actually can be linked together. They are not independent. They are not isolated. They can be linked together by Hooke's law. So this is another way to write the Hooke's law. So it defines the stress equals to Young's modulus times strength. Stress is defined by the force divided by the area, P divided by A. So it means the stress is actually Newton per meter square. And it's actually a force intensity, right? And then strength, epsilon, is defined by net length change of the bar divided by original length. So delta divided by L, that is strength, okay? So here we don't consider change of the area now. In fact, it will change. That will give the difference of true stress and engineering stress. Here we actually talk about the engineering stress. So the force is only divided by original area of the bar, okay? If it's a true stress, then it's a force divided by changed current area, okay? Current area. So here we don't consider it because the area changes anyway is really small, okay? So now this principle always exists there. This principle always exists for the elastic material. And this E is called Young's modulus, okay? So we said it's Thomas Young derived this modulus at the beginning, right? So here is the material behavior. Larger E, stiffer materials are, okay? So when we add the definition of stress and strain into this equation, we have P divided by A equal to E times delta divided by L. Now, because the finite element, we deal with displacement, right? We always solve displacement in the direct method. You saw that already. Based on that, we strike it out some of the rods that has no displacement but unknown. They have no displacement, unknown force, reaction force, right? We strike it out so that we live with the equation set that has a displacement, unknown displacement on the left-hand side. That's actually the reason. So we solve the displacement first in the finite element, right? So then we can put the displacement. This actually becomes displacement because it's net change, right? So this delta goes to left-hand side. This actually is the subtraction of two displacement between left end and the right end, right? So we put it on the left-hand side, delta that is equal to PL divided by EA. Okay, so this actually is a very important equation you will use all the time when you solve the bar element. Okay, now you are not dealing with spring. Spring has only one spring constant, one material property. However, for the bar, even for the same material, they have the same Young's modulus E. Depending on the dimension, L is changing, A is changing. They are the material parameter that links force and the net change, which is related to displacement, actually is not only depending on the material. It also depends on the geometry, dimension, size of this bar element, right? So this actually is the difference between spring and the bar. Okay, and in the future we will talk about the beam. Beam is the advanced version of bar. Those principles always apply, but for the beam you will also have the moment. You will have the torsion applied, so it can have the bending in the object. Okay, so that's how we go step by step to solve more and more complicated object and more close to the real world engineering problem. So once we get this equation, we can see my moving mouse. Yes, excellent. So once we have this, we will study the question that has multiple bars connected together, and for any bar, they can have multiple force applied together. Okay, for the multiple force applied together, any point, the displacement actually will be the displacement caused by each individual force, and then adding them together to sum them together. So total length change of the bar equal to all the different force applied on different bar element that are connected to that point. Okay, different element, different material, different cross section area, summing them together. I is the individual force applied on individual bar element, and then all of them added together yield the total displacement or deformation. Okay, so this is called the principle of superposition. This is always existing when the material is elastic. Elastic means the strength is very small. Delta divided by L is very small, less than 0.5%. So it's 5/1000. So it's very, very small. And that range, the material, we know material consists of atoms, right? Many atoms. At this strength, the force is applied to make the atom to be further apart from each other. So the distance between atoms become further and further apart. And then between the atoms, there are electronic field there because atom is surrounding with electron. So when you change the atom distance, those electron charge can make the atom to attract with each other. And then when you release the force, this attraction force will restore the atom to go back to the original position, original location. And the same principle and vice versa. If you apply the force, compression force, the atom will become closer. And then there is a pushing force. It is generated by the electronic charge. And if you release the force, they will push the atom, all the atoms go back to the original position. This is reversible. So that's why we call it elastic. This is reversible. Within this small strength, 5/1000, that's reversible. If this strength becomes very large, you apply a very large force, larger than this, then the bond, the atom, when they are further and further away, they actually can pass across the neighbor ones. They will pass across. That's in the metal is called dislocation. So they will pass around, they jump beyond the neighbor one, or they actually break. They the electron field are not able to hold those atoms together anymore. They break. But when these things happen, crack happens and the dislocation happens, means they have the shear band there. When these things happen, even you release the force, the atom can never go back to the same location anymore because their position their alignment already changed, permanently changed. So that's due to the plastic region. So in this class, we will not talk about this, but finite element finite element methods are able to solve these problems. Okay, so let's focus on the elastic condition in this class. But if you have plastic questions, those interesting questions, finite element can also do that. Okay, so in terms of the Young's modules, we discussed about the biomaterial in last lecture, right? So those Young's modules are not just a number; they actually can actively trigger cells, especially trigger cancer cells, to make cancer cells to be invasive, right? So there are many important crosstalk, many communication goes on if the material becomes alive. So that's super interesting, and many research opportunities are there to study those questions. Like in my lab, we are studying the different mechanical influence to regulate, to control biological functions, and then those knowledge actually can be used for the therapeutic treatment, right? So go back to the non-alive materials. So let's look at the uniaxial bar, because there are some very important concepts we need to understand about the uniaxial, about the bar, right? Here we talk about uniaxial bar. Can you guys see my mouse? And can you guys hear me? Yes. Okay. Very good. So let's look at those concepts carefully. So this uniaxial bar actually is by definition, is a slender two-force member. It's very slender. As I said, the L is much larger than the diameter of the A, right? Diameter of the cross-section area. So it's very slender, and it's two-force member, means it only can sustain the force at the end, at the two ends. And that force has to be around the axle. You cannot let the force be perpendicular to the axial direction. Then you will cause a vertical force, and you will also cause a torsion, right? Cause a moment there. That is not allowed for the bar entity. That can only be solved for beam element. Use the beam element, you can solve that problem. Okay. So for this one, the length is much larger, at least 10 times larger than the cross-section dimensions. Okay. So and it has only two forces, and it can have varying or changing cross-section area and changing Young's modulus. Means like here, the bar can be taped. It can change the area, cross-section area around the axis. Then you will have change the resistance from the bar, right? That is allowed. That's possible. And the force is always along the axial direction. And it can also change the Young's modulus. Means different material, bar made of different materials can be connected together. That's also reasonable, because the engineering structures, they can have a metal, ceramic, warmed, different material connected together, right? So then if they are slender two force members, they actually belongs to the bar element system. You can use that. In terms of the force applied to the system, it can be both concentrated force, means the force applied on the node, on the one point, or it can be distributed force. Here you see this for F is actually concentrated force applied to one point, right? And then Px is actually distributed force. As a function of X, it is distributed in this middle part, middle cylinder, horizontal cylinder. The force is uniformly distributed. And then this distribution actually can be calculated. And then in the future class, we will show this distributed force can be summarized and then uniformly assigned to the end of this bar, so that we can ensure that only the node experience force, not the element experience the force. And then those force, distributed force can be body force, like gravity, that's the distributed, and the magnetic force, right? That's distributed on the body, right? And there can be many types of this distribution force. And when we deal with this, we can always summarize them and then assign them to the node. Okay. So now it's 115. Is the TA Miao Huang here?
Yes.
Yeah. So TA is here. So we can continue the material and let the TA show you the quiz number 1. You can start to work on that now. Very good, very good. Let's see whether TA has the.
Can you enable?
Sure.
sharing?
Let me see. Yeah, sure. Very good.
Yeah, one student is asking about the time. So this quiz need to be submitted before 1:40, right?
Yeah. All of you should submit the one before 1:40. But some of the students told me they have the other class either issue or other things. That's fine. So those are the exception. You can submit after that. That's fine.
Okay.
Very good. Yeah. So here is one question about the quiz. Okay. Yeah. So where do we submit? TA already write the email to all of you.
Yeah, in the Canvas assignment section, there is a quiz. And you can submit there. Oh, let me create the quiz one right now. You can work on the quiz now, and I create an assignment quiz one.
Do you guys see the share screen clearly? I saw some broken material.
Let me reshare. See if it's...
Yeah. No worry about it.
Is it clear now?
Very good. The TA Miao Huang, since you are the host, you can stop the recording. Stop recording. Just keep sharing the screen. Yeah.
Okay.